sync up the recording, so we'll be recording of this after as well. Should be good. Yeah, but otherwise,
Is that recording?
just gonna triple check. Yes. Yeah. You can see everything between. See like the projector edges. I mean the screen edges.
Yeah. I'll just stick this in there.
Yeah. Oh, alright, take it away. Alright.
Alright, hi everyone. Welcome to the crash course for Eng 2400. It's nice, a couple of familiar faces here, and then there's a whole lot of new people, so that's good. I just want to ask, we've got two options really for today. One is if I just do a recap of each topic, or I pick out a couple of questions from one of the past exams and I do that, or I try and do both. What would you all prefer? Both. Both?
It's an hour.
Yeah, is it an
More
hour?
or less. I mean, you're running the second one as well, so it depends how much you wanna go to that one. But it's fine, by the way.
Well, now till like 12:30.
More or less, yeah.
That'll be enough time, right?
Yep.
I'll try and do both. Yeah. Yeah, does that work? Okay. Alright, so I'll start off with a revision of each topic, and then if there's time, I'll probably go through one or two past exam questions. Okay, so I'll just get started with week 1, and then I'll work my way all the way up to week 9. Okay, so by the way, can everyone see this? Yeah. That's the back? Okay. Alright, so for week 1.
Oh,
Can I just do that? Alright, so in week 1, we did second moment of area, so centroid, and then second moment of area. Okay. Those are the main things that we looked at, and we also looked at product, second moment of area. Okay, so what each of those things are, as a refresher, centroid is really simple. If you have a given shape, say like this, right? Centroid is what's in the geometric center of that shape, basically, okay? And the formula for centroid can be represented from any arbitrary axis. Centroid is represented as y bar and x bar. Okay, so the values of y bar and x bar, by the way, can be anything because it depends. It's y and x with respect to a given axis, right? And so those axes can be anything. It can be at the base of the shape. It can be in the center. It can be something that a question specifies to you where that reference axis is. It doesn't matter. Okay, and the formula for that is for y bar is sum of ai yi over sum of ai. And then for x bar, it's sum of ai xi over sum of ai. Okay, and so you can use that for composite shapes to come up with where the centroid is. And throughout the entire course, for multiple topics, you'll need to know how to calculate where the centroid is. Okay, what I'd recommend you do is, of course, at the start in week 1, you would remember for some of the workshop questions, what you would have done is constructed a table and kind of worked it out slowly that way. Hopefully in the following weeks, towards week 7, week 8, what you probably would have done is you probably would have, instead of using a table, you might have just done it automatically, right? Because you can see the pattern automatically. What I'd recommend is, in a situation like in an exam, do it automatically, right? So you go y bar equals to sum of ai yi over ai equals to, and then just write it out that way rather than doing the table, etc. Because the table is really useful for you to practice and get used to the concept, but when you're gunning it for an exam, just do it automatically. It's faster. Okay, so that's centroid done. Now, second moment of area, you can think about it as resistance to rotation. So let's say this is the y-axis, and that is the x-axis, and this is b, and that distance there is d. Then the second moment of area with respect to the centroid here for an upright square or rectangle is BD cubed over 12. You would have memorized this by now, hopefully. But just remember, this I value is Ixx. So if I make this XX, right? So this is the XX axis, then Ixx is BD cubed over 12. Okay. Now, if I want to calculate the I value with respect to another centroid or another point of reference, which is not here, can be anywhere, say for example it's down here or up here, then I need to add more to that equation. So the general formula for I is I of the individual, sum of I, the individual I value for any particular shape, plus y squared a. Okay, that's the parallel axis theorem. So parallel axis theorem. And basically what that means is for composite shapes, like for a Z shape or an I shape or whatever, you can use the parallel axis theorem to be able to calculate what that is. Okay, that's the basic principle behind the I value. Now the other important thing to remember is Ixy. So that's this last part here, which is product second moment of area. Can anyone tell me here what's Ixy for this rectangle? 0? Okay. So we know that Ixy for a rectangle is 0 when Ixy is taken above the centroid, right? Okay. Can anyone tell me for this rectangle here, Ixy is still 0? Yeah? Okay? Right. Now, if I do this, is Ixy 0 for this? Same shape, still a rectangle. Imagine that's your y, this is your x. Okay? Is Ixy for this rectangle 0? Yes? No? No? Okay. Answer is no. Okay. The thing to remember is Ixy is equal to 0 only for upright rectangles. Okay? The moment your rectangle is rotated like this, Ixy is not equal to 0. Okay? Now hold that thought. That is product second moment of area. Now, by the way, if you wanted to calculate the product second moment of area for a composite shape, we can also write the parallel axis theorem. So this is the Ixx parallel axis theorem. The Iyy parallel axis theorem is Iyy equals to the sum of all individual Iyy's plus x squared a. And Ixy is the sum of all individual Ixy's, right? Plus x, y, a. Okay? So this is all the parallel axis theorem. They're just with reference to different axes. So for Ixx, that's the parallel axis theorem. Iyy, that's your parallel axis theorem. And this is for Ixy. Now what you might remember is from the workshop questions that you would have done for this topic. If say you have a Z shape like this, for example, that's your composite shape, right? And you had to calculate, let's say Ixy for this shape. What would you do? You would split it up into different shapes, parts. So let's call this shape 1, we call this shape 2, and this is shape 3, right? We're going to split it up in different parts. We have to first identify where the centroids for each of those individual shapes. So that's centroid 1, centroid 2, centroid 3. We also have to identify where's the centroid of the entire shape. So using those formulas over there, we can say, let's say for example, it's over here, that's the centroid of the entire shape, and then we chuck this formula in, right, to calculate the Ixy for the entire shape. So how would we do that? We first need to ask, what's the Ixy for all of the individual shapes? Because these are all upright triangles, it's all 0. So that's Ixy is 0, 0, and 0 here, so this entire term goes to 0. Now I want to calculate what's xya for each term. So for shape number 1, x is this distance from the centroid to this shape, and y is the y distance from the centroid to this shape. That's for shape number 1. Okay, so your first term will be x, y, a for shape 1. Plus, you do the same thing, x, y, and a for shape 2, x, y, and a for shape 3, and that's your product second moment of area. So that's how you calculate product second moment of area. The same concept applies for when you do Ixx and Iyy. Okay, if you're still a bit rusty on this, because it has been what, like 9 weeks since you've first learned it, go back to the week 1 workshops. I recommend just practice those questions. Okay, there's plenty of these kinds of questions in the week 1 workshops. But that's the main idea. Now the last thing that we covered in week 1 is the Mohr circle. Okay, so the Mohr circle is every combination of Ixx, Iyy, and Ixy value for a given shape. Okay, so that's it. The y-axis is Ixy, and the x-axis is Ixx and Iyy, and let's say that's your Mohr circle, right? Your principal second moments of area are here. Let's say this is I2, this is I1. Those are your principal second moments of area. And every point on this circle is every combination of Ixx, Iyy, and Ixy, right? So let's say, for example, you have this rectangle here. When the rectangle is horizontally upright, you start from here, right? And as the rectangle rotates, you start to go around the circle, right? When the rectangle is upright, you're on this side of the circle. You keep rotating the rectangle, it goes across the circle, and now when you're back flat again, that's on this side, right? So for the same shape, for every rotation of that shape, the circle covers every combination of Ixx and Iyy for that shape, right? So that is the Mohr circle for the second moment of area. Now, the good thing is we also have, if you have a look at your notes, there are the transformation formulas. For second moment of area. Okay, so what that means is for a given angle of rotation, that's called the angle of rotation theta. For a given angle of rotation, you can find the new Ixx or Iyy or Ixy. I'm not going to write the formulas up here. There's 3 or so different formulas. They're in your lecture notes. Go have a look at them and keep them on hand in case you need them, right? These are your transformation formulas for second moment of area. They're very similar to the stress transformation formulas from your Mohr circle. Okay, so given a particular angle, let's say in real life you're rotating it, say 20 degrees anti-clockwise, for example. That means this would be your 20 degree, theta would be 20 degrees. And then from that you can calculate what Ixx, Iyy, and Ixy is, the new values. Okay, so those are your transformation formulas. So back to the question I asked earlier, Ixy for this is 0, right? Sorry, it's not 0 because it's kind of rotated sideways. So the question is, how would I actually calculate what Ixy is for this? What I can do is I can start with a direction that I know. So I know about this line facing this way, Ixy is equal to 0. Because about this line it's upright. Okay? Then what I can do is I say, all right, I'm not interested in this direction, I'm now interested in this direction. I need to rotate this by this angle theta, or by this angle theta. Okay? Or I suppose the other way around. By this angle theta, by this angle theta, right? Starting from this line, I need to rotate it this way. And I can drop in my transformation formulas to transform it to calculate the new Ixy, okay, using the theta. So starting from 0, you rotate and you get the new Ixy value. That's how you will calculate Ixy for shapes that are inclined, okay? Now the most important thing is the rules of the I-value Mohr circle. Okay, And this is the way I teach it in my class, is there's two sets of situations, right? You have what's happening IRL, real life, versus what's happening in the Mohr circle. Okay? Now, when you're rotating by an angle theta in real life, in the Mohr circle, it's double that. So in the Mohr circle, it's 2 theta, right? And if you have a particular direction of rotation, say anti-clockwise in real life, in the I value Mohr circle, what is the direction of rotation? Clockwise? Clockwise, everyone agree? That it's opposite? You sure? Okay. Now this is why I like to bring this up, because what you're referring to are the rules of the stress and strain Mohr circle. The stress and strain Mohr circle, yes, they are opposite directions. But for the I value Mohr circle, it's actually the same direction. An anti-clockwise rotation in real life is also an anti-clockwise rotation in the Mohr circle. Okay, so I'll draw out an example for you. Let's say we have this shape here in this direction, like this. That's the center of the shape. This is Y and this is X. Let's say this shape here in this orientation here is occupying this point on the Mohr circle, let's say. Okay? If I take this shape and I rotate this shape clockwise, like this, okay, and if the clockwise rotation was, say, 30 degrees rotation clockwise, then what you will see is, so for example, let's say this is scenario A and this is scenario B, right? Scenario A, by the way, for any given scenario, you always have 2 points on the Mohr circle. So any given scenario, you always have, it's a plane on the Mohr circle. This is scenario A. Okay? If in real life I rotated 30 degrees clockwise, in the Mohr circle, I'll rotate 60 degrees, but I'll also rotate clockwise. Because this is the I value Mohr circle. It's the Mohr circle for the I values, not for stress and strain. Okay? So that means that there's also a clockwise rotation. It'll look something like this. 60 degrees. And this is scenario B. Scenario B. Okay? Now always remember the points that you're actually plotting on your Mohr circle for any given system is IXX and IXY, IYY and negative IXY. These are the coordinates that you plot on your Mohr circle. Okay? The coordinate that corresponds with IXY is the positive, with IXX is the positive IXY. The coordinate that corresponds with IYY for the x-axis, x value, the y coordinate will be negative IXY. Those are the coordinates that you plot on your Mohr circle. That's why every given orientation always has 2 coordinates, right? That's why it's a straight line on the Mohr circle. Okay, that's the main thing from week 1. Okay, any questions on this? Cool. Okay, let's move on to week 2. Okay, can I wrap this up? Can I erase this? Now we have week 2. For week 2, we covered stresses. Now the idea behind the Mohr circle for week 1 and week 2 is very similar, only with some slight changes. Okay, so let's have a look at week 2. Remember, stresses at the end of the day are force over area. Now, before we go any further, I just want to remind you again the combinations of units that work in a given formula. Okay, there's 4 preferred combinations of units and you can choose any one of these combinations. So for example, force, length, pressure. Okay? If you just want to use SI units, you can for any given formula, okay? So if your forces are in newtons and your length are in meters, then your pressure will be in pascals. Okay, that is one combination of units that you can use. Okay, the next combination is you use kilonewtons for your force and you use meters for your length, then your pressure will be in kPa. Okay, that's the second combination that you can use. Now, less common combinations, but what I feel are more relevant to what we're doing in this course. If you use newtons for your force and millimeters for your length, then your pressure units are going to be in MPa. That's the most common. I prefer to use this one most of the time in this course because I know it's solid mechanics, which pertains to many different types of engineering, but it's generally this term is being run more so from the civil stream, which means it's relatively related to structural engineering. So in structural engineering, generally speaking, like for buildings and stuff like that, most of your cross-section dimensions, most dimensions in general, usually given in millimeters, and most elastic modulus, etc., are all usually either given in MPa or GPa. Okay, so that's why I prefer not to stay in these two combinations at the top. I prefer to use this, or if you're using kilonewtons for force and you're using millimeters for length, you can use GPa for your pressure. Okay, any one of these. I prefer these two, usually the first one, the MPa one, but then you can use the GPa one if you want. Okay, now the main thing for stresses is your Mohr circle. So let's say we have a stress element like this. This is the y-axis, and this is the x-axis. Okay. Now I'm going to give you a few stresses, and I want to ask you what sign those stresses are. Okay. So imagine you have a stress block that looks like this, and these are the stresses on it. Okay. Imagine you have a stress block that looks like this. All right. Can anyone tell me what is sigma xx? Positive or negative? So is that tension or compression? Tension. Okay. So this is 4 MPa. All right. Sigma yy? Positive or negative? Negative. Right. Compression? Okay. Negative 3 MPa. All right. Tau xy. We know it's 1 MPa. Okay. Positive or negative? Positive. Okay. So if you were to complete the arrows like that, you have on this side it'll be going this way, and then on this side it's going this way, so that is positive 1 MPa. Does everyone see that? Right? You have to sort of memorize what the directions are for a positive shear, or what the directions are for a negative shear. Okay, and it's really important because it'll change your sign convention in your numbers completely if you get it wrong. So just remember, if your top two arrows are sort of pinching the right hand corner, your bottom two arrows here are pinching the left hand corner. So if bottom left and top right are being squeezed like that, that's positive. And if it's top left and bottom right that's being squeezed by the forces, then it's negative. It's an easy way to remember what the combination is. Okay. All right. So that's what this is. Okay. Now I'm going to draw out the Mohr circle. So tau xy on the top, sigma xx, sigma yy, and I'm going to draw up two scenarios. Okay. I'm given you two scenarios on the Moore circle. There's scenario A and there's scenario B. For the stress block that you're seeing right now, can anyone tell me what scenario it is on the Moore circle? Is it A or B? Let me just move the y-axis across because of the signs. Let's say we do something like that. Okay. Can anyone tell me, is it A or B? A? Do we all agree? Is it A? Is B? Okay. Let's ask ourselves first, what are the coordinates that I have to plot? Remember, it's the same thing as I value Moore circle. The coordinates that I plot are sigma xx and tau xy, sigma yy and negative tau xy. Okay? So sigma yy here is 4 and tau xy is 1. Sigma yy is negative 3 and the negative of tau xy is negative 1. Okay? So, A or B? B, right? So remember, that's how you figure out where you are on the Moore circle. Remember, for any given state, the points that you plot on your Moore circle are these, right? So, in this case, this would be scenario B, right? Because this will be negative 3, negative 1, and this side will be 4, 1. That's how you plot it on the Moore circle. Okay? Now, again, for stress Moore circle, you also have your stress transformation formulas. Okay? So what are the few stress transformation formulas that you know? You first know that you have theta p. The formula to get the angle that you've got to rotate to get to the principal axis. Remember, the principal state is the x-axis. That's the principal state. That's the theta p formula. You also have formulas for ixx dash, iyy dash, sigma xx dash, sigma yy dash, tau xy dash. These are formulas which are in your notes using any given theta. It doesn't have to be theta p, it can be any theta, any angle you wish. These formulas will help you transform the original sigma x-axis to the new sigma xx. Okay, or yy or tau xy, whichever you want to call it. Okay, so those are your stress transform formulas that you've got to keep in mind. Now, the rules for the sigma and the strain Moore circle, okay, they both have the same rules. Okay, now you have your IRL versus what's happening in the Moore circle. If you rotate by an angle of theta in real life, you will rotate by an angle of 2 theta in the Moore circle. That's true. Okay. Now, if you rotate by, say for example, an anti-clockwise direction in real life, in the Moore circle, you will rotate in a clockwise direction. This is what you have to remember. Okay, which you pointed out correctly before. The direction is flipped for stress and strain Moore circle, but importantly, the direction is not flipped for your I value Moore circle. Okay. You got to keep that in mind. So we can do another example here. Can I raise this Moore circle up? Yeah. Okay. So okay. Now, let's say this is the Moore circle for this shape, right? And I've plotted in the points correctly, that's what it is, right? That's what it looks like. Okay. Now, let's say if I were to draw two versions of this, I'm going to draw an axis in green, and I'm going to draw an axis in red. Something like that. Okay. Can anyone tell me which of these axes, the red one or the green one, is the principal axis? Red or green? Red? Any, green? Anyone? Red? Okay. Anyone? You guys? What do you guys reckon? Green? Okay. Alright. Look, question is you gotta ask yourself, in the Moore circle, how did you rotate to get to the principal state? Right? In the Moore circle, to get to the principal state, which is on the x-axis, you had to rotate this way. Right? So you rotated clockwise to get to the principal state in the Moore circle, which means in real life your axis rotated anti-clockwise by half the angle to get to principal state. Right? Which means it's more likely that the red axis is the correct one as opposed to the green one. Okay? This is really important, by the way, because this forces you to kind of conceptualize what the understanding is without doing any calcs, without doing any numbers. It's important as well because once you do the calcs, you should be able to look at it and just kind of be like, yeah, that makes sense. Or if it's opposite to what you reckon, then probably made a mistake. Yeah.
So say like the stress, the sigma x and the sigma y were like flipped. So it would be scenario A as you had before, and the line was going diagonally like this.
Yeah.
Or like this way. Then would the angle be rotating counterclockwise, and then in real life it would be rotating clockwise?
Yeah. So it'd be green, yeah, be the other one.
Or would it? And does like when you're rotating it from, so say if that's 30 degrees right now.
Yeah.
If it was 60 degrees and it's closer to the y-axis, would you still be rotating it?
No, so it depends. Remember, that's a really good question because it sort of becomes arbitrary, right? Which axis is your point of reference? You've got to ask yourself, what point is this for one? Is this the x point or is this the y point?
The x point.
The x point, correct. So this is point x. That is your point y, right? To get to the principal state, your point x rotated by this angle, right? To get to the principal state. That means what was your x-axis before needs to do a opposite rotation in real life of half the angle to get to its new x point, which means this x-axis became that.
Yeah.
And vice versa. Yeah.
Okay. Yeah.
Does that make sense?
Yeah.
That's your question.
Just clarifying.
Yeah.
So if so say that's angle is 60, is 30, and then it goes up to 60, right? Then it would still be going down that way.
Sorry, you're saying this is 30,
Yeah, and then
this is 60, yeah.
and then but if it was like the ratio was flipped instead, so
Oh, you're saying if it was like this.
yeah,
Yeah.
then would it still be going down this way, or would you be able to like reference it to shear?
Well, the question was, what's the rotation to the principal state? The principal state is the x-axis, not the y-axis. So it's basically what angle do you have to rotate by to slam it down to the x-axis? Yeah. So there's two ways to do it. You either bring it to the x-axis this way, or you bring it that way. Regardless, you end up with the same. Cool. All right. Any questions on stress? That's basically it, pretty much, what stress is. Okay. All right. Let's move on to strain. Can I erase this off? Yeah. Okay. looked at strains. Now, for strains, the rules between strains and stresses are very similar. There's only a couple of things that I've got to point out. First of all, let's say I've got the Mohr circle here, and I have a stress block here. Okay? Now I'm going to try and draw out here a couple of strains. So let's say this is okay. I've drawn out a stress block, all right, and I've applied some strains to it, like you can see here, and I've drawn out the Mohr circle for this situation. Okay. Now, can anyone just have a look at what I've done quickly and just tell me if I have made any mistakes?
0.01.
Sorry?
The sign convention.
Sign convention. Okay, so you're saying it's supposed to be
Negative.
negative. Okay, so that's negative, positive. Okay, so it should be, instead of that, it should be like this.
Yeah.
Okay, so this is negative 0.02, negative 0.01, and 0.04, 0.01. Great, okay. Any other errors?
You should divide it by 2.
Very good. Remember, the y-axis always has to be gamma xy divided by 2. Like, believe it or not, this is like one of the most common mistakes that are usually made in the final exam by students over the past few years. Okay? For strain, whenever you're looking at the Mohr circle, this needs to be divided by 2. Everything is in terms of divided by 2. So what you'll find out is your strain transformation formulas, by the way, which are almost identical to your stress transformation formulas, there'll be one small difference inside. Two small differences. Every time you see gamma xy, instead of a positive sign before, it will be negative in the formulas. And the other thing you'll realize is everything will be in terms of gamma xy over 2. Okay? Like the form of the formulas will pretty much be the same, but those specific changes will be there. So just make sure you take those into account when you're drawing out your Mohr circle. So that would mean that the coordinates that you plot over here, instead of negative 0.01, it'll be negative 0.05, and this would be 0.5. And that's what you end up plotting on the Mohr circle. So that Mohr circle is basically wrong, what I've done. Okay? That's for strain. Now, the other thing that we've learned in strain is the strain rosette. Okay? For strain rosette, the idea is basically, you know, say for example, you're given a particular combination of different strain gauges. Let's say something like this. Right? Given a particular combination of 3 strain gauges, and let's say this is your x-axis, and that's your y-axis. Okay? If you know what the values of each of these are, strain A, strain B, strain C, okay? And if you know what these angles are, theta A, theta B, theta C, there's a set of formulas that you have, and you can work out what epsilon xx, epsilon yy, and gamma xy are. So generally what you'll see, the way you'll see strain rosette stuff in questions would be, it'll be like the first part of the question, right? They give you a combination of strain gauges. They're like, okay, have a look at these strain gauges that are pointed in different directions, calculate what epsilon x, x, y, y, gamma xy are, and then after that they'll lead you into the more circle stuff. Okay? Or it can be Hooke's law stuff, however they wish. So like these questions tend to be like compound type questions. And the strain rosette is generally the first part. It's not meant to be difficult, right? It's not meant to be a trick. Just make sure you have those formulas on with you. And for strain rosette, remember there's a couple of special case scenarios, okay, which make the formulas very easy. The special case scenario, so special case is if you have a 45-degree strain rosette, like this, or like this, where this is 45, that is 90, or this is 45, and that is 45 as well. These are your special case strain rosette setups. The reason why these are special cases is because if your epsilon A, B, and C are oriented in this direction and you've got angles like that, it simplifies your formulas into a very easy version of the questions, okay? So if you have that, then just remember to use the easier version and you should be good.
Just a time check. It's 5 to
Yeah,
12,
fine.
so 5 to
No, that's all right. Any questions on week 3 strains? Okay. Now, very quickly, I'll touch on Hooke's law. Now, what you probably find is, I think it might be better as well, is, and this is what I did for my classes when I did the tubes in the last session. I did a revision like this, but instead of doing it for every single topic, I specifically paid a bit more attention to the earlier topics because it might be probably less fresh in your memory from like a few weeks ago. Okay. So the next one is Hooke's law. Okay. For Hooke's law, the main thing that you've got to have a look at is the difference between stresses and strains and how they're linked. Okay? In one dimension, Hooke's law is given by this formula. Okay? But in this course, we don't deal with the one dimension version, we deal with the 2-dimension version of Hooke's law. Okay? Which means, so this course, we deal with 2 dimensions. Okay? In the 2-dimensional case, what we're really looking at is, so say for example, something like this. Okay? Now there are 3, remember, every question or every situation you're looking at in this course anyway, when we're looking at Hooke's law, we deal with it in 2 dimensions. There's also 3 dimensions. Okay? Now the 3-dimension version is the generalized version. Okay? You have the formulas with you, they're in the lecture notes. Basically, it's a bunch of formulas showing every single direction, x, y, and z, and tells you how to convert xx, sigma xx, to epsilon xx, and yy and zz. The reason why we don't use this formula directly just as is because for a 2-dimensional case, that's too simple. Okay? If you stress or strain something in one direction, the other directions aren't unaffected. They are going to be affected as well. And because of that, you have a generalized set of formulas here. Now, thankfully, the course also has a few 2D special cases. Okay? The 2 special cases that you've got to remember are plane stress and plane strain. Okay? Now, the trick behind this topic really is just to identify what situation you're in. Are you in plane stress state or are you in plane strain state? That's it. Those are the main things you've got to identify. Once you've identified that you're in plane stress or that you are in plane strain, the question becomes very easy. Okay? Because after that, you just have to chuck it into the formulas, the appropriate formulas, get your answer and move on. Okay? So that's the real trick behind here. Sometimes the question tells you, sometimes it's your job to figure it out. That's the point. Okay? Now, plane stress means that your stresses are only applied on a plane. That means you only have stresses in, say, the x and y direction, but you don't have any z stresses. Okay, that does not mean that your strains are only in two directions as well. It just means that your stresses are in two dimensions. It can strain in however many dimensions it wants. So for example, this case here, okay, if you've got a plate that's just sitting on the floor and you're pulling it this way and you're pushing it that way, but there is no out of plane action, that is a plane stress case. Another example of a plane stress case would be a column in a building, right? Let's say this is the edge of a building, right? And there's loads that are applied on the top here. All these loads, when they go into the column, they come in like that, right? That's how the axial force moves, right? This is only in one direction. There isn't any force pushing into or out of the page, right? There's no other forces except for this. So this cross section here in a building is only going through sigma z, right? And sure, if you want to push it into the page as well, you can if you want, it doesn't matter. As long as the stresses that you're applying onto your object are only in two directions, you're in plane stress. Now, how do you identify plane strain? Plane strain is most common when you have an object or a structure that has an indefinite length or a very long length in one direction. Okay, so I'll give you an example. A retaining wall that runs into the page for however long distance. So say for example, or like a dam, right? So you have a dam here like that. And it is holding back all of this water. Okay, and the dam runs into the page for a very long distance. Okay, so the dam runs into the page. It's holding back all this water. The only way this dam can strain, like move, the only way it can move is this way, right? Like the dam is sticking up, the only way it can move is rotate that way, right? The dam, see, imagine this dam is moving out of the board like this, right? The dam won't buckle this way, right? It will only just curve in one direction. Why? Because it's a lot stiffer into the page than this way, right? Because it's got a very, very, very long distance into the page. So any structure that has one of its dimensions much longer than the other, most likely would be in a plane strain case. Another example of plane strain would be a tube. If you've got a tube and it's full of water or pressure that's building up, but the tube runs into the board forever. Okay? So it's like a hose or something, right? And then you spray high pressure water through it. What will happen is the hose will want to expand outwards, but that's it, right? It won't expand into the page because that distance is super long. It just pushes outwards, right? Hydrostatic pressure pushes outwards. So that is also plane strain. So just remember that plane strain. Of course, for every situation, have a think about it. Ask yourself, does it make sense? Remember, plane strain is strain only in two directions. Stresses can be everywhere, it doesn't matter, but strain only in two directions. That is plane strain. Plane stress is stress only in two directions. Strain can be in however many. Okay. Plane strain, if you have an object that has a very long distance into the page or in a given direction, tends to be plane strain. Plane stress is easier to see. Okay. Any questions on Hooke's law? That's it for Hooke's law. Week 4. Special stuff to remember. Okay. All right. Now let's have a look at week. Can I erase it? Yeah. Okay. For week 5, we had bending stresses. Okay. Now, bending stresses essentially being if you're taking a beam, right, and you're bending it, you have one side will have compression and the other side will have tension. Okay. So let me give you an example. If you have a fixed end on this side, so you've got a cantilever beam. Okay, let's say you've got a cantilever beam and you have a load that's applied on the top. Like this. Okay? First of all, can anyone tell me which part of the beam experiences the highest bending moment, internal bending moment? The fixed end or the free end? highest internal bending moment? The left hand side, the fixed end, or the free end on the other side? Free end? Anyone? What do you guys reckon? Oh, you did it. He said.
Yeah,
Okay.
yeah.
What do you reckon? Fixed? You say fixed as well? Okay, free? Anyone here? Free? Fixed? Fixed? Okay. Again, this is a revision from Eng 1300. If you draw the bending moment diagram for this shape, it looks like this. Okay? The fixed end has the largest internal bending moment and the free end doesn't. Okay? Now, how do you calculate what is the maximum moment here at the fixed end? You literally just take the entire load multiplied by the lever arm, which is halfway across. That's it. That's the maximum moment that's experienced. Okay, next question. For this beam, cross section that is all the way towards the end, I'm talking about this cross section here. Can anyone tell me what stresses are experienced on the top fiber of the cross section? Is it tension or compression? Tension? 100%, are we sure? Yeah. Tension? Compression? Tension? Yeah? Okay. Look, whenever you have a beam, or any shape for the matter, and it's bending downwards, which means it kind of does this kind of curved shape like that, right? The top fiber will want to separate and pull apart. Top fiber does that. Bottom fibers pull inwards together, so it pushes in. So the bottom fiber is in compression and the top fiber is in tension. That's the same thing that's happening over here. When this entire thing wants to bend, the top fiber goes in tension, the bottom fiber goes in compression. So the stress diagram, the bending stress diagram for this is like this. Okay? Let's say this is the tension side, that's the compression side. That's what it'll look like, right? This is the top half, which is in tension, the bottom half, which is in compression. Now, a couple of things to note. If your entire structure, or if your entire cross section is completely elastic, for a fully elastic cross section, then the formula to calculate your stresses in different elevations of the beam are sigma equals to negative my over I. Okay? So for example, for a given bending moment across an entire cross section and a given y distance away from the neutral axis and a given I value for your entire cross section, you can use this formula to calculate what your stresses will be at any point along the element. So you can calculate that stress if you want, that stress, etc. But the rule is it has to be completely elastic, meaning nothing should have yielded. Okay? That's the basic part of a single material. Okay? The next thing that the course looked at was a composite material. If you have a composite material, say something like this, where you have timber here, and let's say you've got steel here. Okay? So let's say you have this cross section. Okay? You have steel at the top and you have timber on the bottom. And let's say the question asked you, when you're doing these calculations, convert everything to steel. Okay? So let's say the question says, convert everything to steel for the calcs. Okay? If you had to draw out the cross section again, I'm going to give you two options. What would it look like? That is option A, and this is option B. Can anyone tell me what it would be if that's your material, that's your cross section at the top? And by the way, just to jog your memory a bit, elastic modulus of steel is much higher than the elastic modulus of timber. Okay? Steel is the stronger material, it's the stiffer material. Okay. So if you've got a steel plate on the top and the rest of your cross section is timber on the bottom, and the question asks you to convert everything to steel, what would my transformed cross section look like? Would it be scenario A or scenario B? A? A? Anyone says B? Are you sure? I'm going to double check with you. Steel is the stronger material compared to timber. Yeah, it's A. Okay. Alright. So remember, the weaker material, so just this is the concept you've got to remember. The weaker material needs more volume to do the same job as a stronger material, right? So if you're converting the weaker material, timber, to the stronger material, you shrink it. Because a thin strip of steel this way will do the same job as a thick piece of timber this way, okay? Now remember the flip side of that as well, the other way around. If the question asked you to convert to convert everything to timber, okay? So if the question asks you to convert everything to timber, what would you do to this steel plate on the top? Would you shrink it down or would you expand it? Expand it, right? Because a larger piece of timber, you need a large piece of timber to do the same job that a small piece of steel requires, okay? How do you calculate your modular ratio N? Remember, N is elastic modulus of what it was before over after. So in this question here, if I have to convert everything to steel for the calculations, to convert this timber to steel, my N value is going to be elastic modulus of timber on the top and steel on the bottom. If the question asks you to convert it the other way around, then you're going to flop it. In one of the recent past year papers, if you would have noticed, one of the questions that was asked was something that looks kind of like that, and you have to convert to the stronger material. So you've got to convert everything to equivalent steel. Now the problem with that was, most of the time in the workshop questions, you are always converting the weaker material to the stronger material. Okay? Oh, sorry, the other way around. The stronger material to the weaker material. Most of the time in your workshop questions, N was a high number. It was positive, and it was more than 1. Okay? But in the exam, in that particular year, because they asked you to do the reverse conversion, N was actually lesser than 1. It was a smaller number, and that caught out a lot of students because they did the wrong conversion. They did it the other way around from rote learning. Okay? So keep this in mind. Read the question carefully. If there's a certain type of conversion, then you've got to follow suit, and this is the formula that you use. Okay? Now the next question I'm going to ask you is, for the same strain, which material has more stress? The steel or timber? Steel? If you've got a plate of steel and a plate of timber, they're both experiencing the same amount of strain. Which one has larger stress? Sorry? No. It will be steel. Remember, for the same strain, the stiffer material accumulates more stress. Why? Because elastic modulus equals to stress over strain, which means stress is equal to elastic modulus times strain. For the same strain, if your elastic modulus is higher, steel has an elastic modulus that's higher than timber, then steel has a higher stress. Okay? That's the basic part of bending stresses. Okay? Mind you, being a very popular topic to be tested in exams. Okay? Any questions on this? Okay.
What's the N stand for again, sorry?
Modular ratio. Now, week 7 was Okay. Now the next big topic that we looked at for solid mechanics was deflections. Okay, so now we're coming on to the last few topics or weeks within the subject. This topic really had two things that we were looking at. The first part of it was your axial deformations, and the second part of it was your bending deflections. Okay. Now I'm not gonna go through all of the details behind each of these topics, but there's a couple of things that I want to point out to you about each topic that you should pay special attention to. First thing is for axial deformations. We know that the formula for axial deformations is elongation equals to NL over EA. Okay? Now, this formula only works if over a given distance L, N, E, and A are constant. You must remember that. This formula only works if over a given distance L, the force N, elastic modulus E, cross-section area A are constant. If any of these values change over your length, you have to integrate it. Okay? So I'll give you an example. If you have a shape that looks like this, and you're pulling on this, okay, you can't use this formula directly because cross-section area changes across the length, right? So the thing that changes needs to be integrated. So what do? You name a given x direction in a particular direction, like that. And in this case, you're right. So what are the things that are constant? In this case, let's say n is constant, so n's outside the integral. E is constant, so e is outside the integral. Then we chuck the integral sign on. A is what is changing. So A is changing, and you're integrating this with respect to length, which is x. So that's your L. It's the same formula, except you just have to remember that when you do the integration, this is how it's going to look like. The other thing about the integration that you need to keep in mind is if the question ever gave you density or unit weight, what that means is your material has got a weight to it, and you have to include that in your calculations as well. A popular version of that is if you have something that's hanging from a fixed end at the top. If you have a load here that has a certain axial load here, say it's 40 kilonewtons or 50 kilonewtons or whatever, right? But this thing is a heavy rod. You also have to take into account the fact that there's gravity that's also pulling this down. Is the gravity constant? Yes, the acceleration due to gravity is the same, but the force isn't constant. Why? Because at this cross section, there's no mass below it. Because I'm all the way at the bottom. There's no mass below it, which means there's no weight. At this cross section, yes, there is weight. In fact, there's weight of everything below it. So the weight of this shape changes from this point all the way to this point. So in this formula, n is non-constant. So n needs to be integrated. Everything else is constant, so you can chuck that outside the integral. Okay. This is if a density or unit weight is provided. Okay. Those are for axial deflections. Now, for bending deflections, I'm not really going to go through it. There's an entire recording of the workshop for bending deflections, which is on Moodle. Literally, just right on the home page, it says week 7 demonstrations. If you have any concerns about that particular topic or how to solve it, there's a full recorded demonstration that's in there. Really useful. You can check that out. The one thing that you have to remember is when you're usually bending deflections is a huge topic in the course, right? And it's one of the harder topics, and generally it's one of the ones that are tested. Okay, so pay special attention to that. Do as much practice as you can for that. I'm not covering it now, but it doesn't mean it's not important. It definitely is important. This is something that you have to work on, right? And remember, in bending deflections, to me, the hardest part that you've got to train for really is your step functions. Okay, practice writing out the step functions for different structures and different shapes. Okay, and once you have your step, if you're able to correctly write out a step function for a given structure, the integration and stuff is not that hard. Okay, you'll get through that pretty fine. Okay, now after this, the last two topics in the course, which I'll discuss briefly, are shear and torsion. Okay. The last two topics are shear and torsion. Okay. Again, I'm not going to go through in specifics what each topic is about, but a couple of important things to point out. Firstly, for shear, this is a common thing that is a common misconception about this topic. We know that there's the popular formula here, tau is equal to VQ over IT, or VQ over IB, however you spin it, it's the same formula, right? This is the formula for shear stress. Okay? Now, there is something else that's known as shear flow, right? Shear flow has a similar formula, okay? It's usually denoted as Q, and shear flow is VQ over I. Almost the same formula as this, except there's no T, right? But it is quite easy to misconstrue as to what shear flow actually means, okay? Shear flow. The most important thing that I want to point out about shear flow is the direction of shear stress and the direction of shear flow are two completely different directions. Okay, they're not the same. I'll give you an example. Okay, if you have an I-beam like this, and the I-beam is going through some bending into the page, okay, so if I draw the beam out in elevation, it's supported on both sides like this. Let's say there's a load that's applied and this entire beam is bending this way or this way, right? Then what would the shear look like in this beam across the cross section? It'll look something like this. Those are your shear stresses. Okay. Now, using the first formula here, tau is equal to VQ over IT, we can calculate where these stresses are, right? Or how much these stresses are. Because remember, if I were to graph out how the shear stresses change from the top all the way to the bottom of the shape, it looks like this. Okay. The web, the middle part of the cross section, takes in the most shear, experiences the most shear, right? So how do you calculate the shear stress on any point of this curve? Okay. To calculate that, all you've got to do is first note where the centroid is, right? And let's say I want to find the shear stresses right here. Then, if you recall, what you would do is you will take a cut. And remember, your cut needs to be perpendicular to the direction of the shear flow. So in this case, the shear is moving down this way, so my cut is perpendicular to it. If I wanted to find out how much shear stresses there were across this cross section here, then my cut is going to be like that. Vertical, right? Because the cut is always perpendicular to where the shear flow is. Once you make your cut, you can redraw the shape here, like that. What you would have to do is you'd have to draw out your structure from the cut to the extreme ends of the cross section, and you can calculate VQ over IT. That's fine. If you notice, the direction of VQ over IT is moving up and down across the cross section. Yeah? We only deal with the cross section for shear stresses. But when we are talking about shear flow, which is VQ over I, you must understand that the direction that we're talking about isn't up and down anymore. The direction we're talking about is into the page. Okay, that's very, very important. So questions like, how strong does the weld have to be? How many nails do you use to connect this thing and that thing? Those are all related to directions into the page, right? Because if, let's say I've got 5 nails that I'm applying to the beam, those nails are all, let's say, here, like that's a nail, right? The direction I'm interested in is into the page, because I'm going to be nailing 5 nails into the page, right, at different spacings. So remember, VQ over I calculates the shear flow at a given point. Let's say I can calculate the shear flow here, just use VQ over I. But that gives me, in newtons per millimeters or whatever the unit is, the shear flow into the page. Okay, so remember, if you have a beam here, I'll just write it down here. Shear flow is in the direction into the page. Shear stresses is in the direction across the page. Okay. Now the last thing that I want to cover before we wrap it up today is torsion. Okay. Torsion is really a simple topic. Okay. At the end of the day, there's only one form, or there's 2 formulas that you use, and you toss them up, based on that. The important things that you got to get good at for torsion questions. Number 1, drawing the torque diagram. Okay. The one thing to know is for torsion questions, drawing the torque diagram is similar to shear force diagram. The concept behind drawing a torque diagram is similar to a shear force diagram. Now have a look at the questions in the workshop. Try them out yourself. That's really important because a torque diagram tells you how much torsion is experienced by a given beam at a particular point. Okay? That's the first thing you've got to remember for torsion. The second thing that you've got to remember is J. Formulas. Okay? J is a material property. It's like I, right? J is your polar moment of inertia. Okay? Every shape has its own J formula. The one that you would have used a lot or most of the time in this course is J for a circle. Because most of the time for torsion, you're dealing with like a cylindrical shaft or something like that in most of the questions. Okay? Just note that J has different formulas for different types. So for example, get acquainted with the formula for a hollow cylindrical shaft. Okay? It's not the same as if it's a solid circular cross section. Other things you can look at, if you've got a square, cross section, and there's torsion that's been applied to it, how do you work on that? Again, just in your notes, keep the different J formulas. And apart from that, you should be pretty solid for torsion. Okay. Now, the one thing that I do have to note is a possible way of asking these kinds of questions for torsion is by linking torsion. Well, remember, what do you get from torsion? When you apply torque to it, you get shear stresses, right? You get shear stresses at the extreme ends or at the extreme outer ends of your cross section. If you apply a normal stress also, so say for example, I have a pillar or like a bollard or something that's sticking out of the ground, it's circular, right? And I apply a downward load on it and I twist it at the same time. What's happening? I'm inducing shear stresses on the outer edges and I'm pushing down the bollard, which means there are 2 stresses that it's experiencing. Normal stress and shear stress. Now, what's stopping you from drawing out a more circle for that question? Because now you have a combination of shear stresses and normal stresses. That's a possible combination for you to be able to tie in your shear stress understanding from torsion all the way to the more circle type question. Okay. In fact, that's in one of the workshops, in the last workshop. So have a go at these different types of questions and practice. The most important thing to look at, in my opinion, is if you haven't started your revision yet or you've just kind of started, maybe think about this flow of events. First of all, have all of your notes that you're going to bring into the exam with you when you're practicing, right? I really wouldn't recommend for the final exam bringing in like a huge stack of notes or finding a similar question, because the odds of a similar question coming out is very low, and I wouldn't put my odds on something like that happening. Okay, so like just don't do it. Now, what you can do is important formulas, stuff like that. Have those with you, right? And practice with those same set of formulas and same set of notes so that you can use it efficiently in the exam. That's the one thing. The next thing is when you're recapping for the course, what I recommend you do is first start off with the quiz that's on Moodle that Elena had put together for final exam prep. Okay, if you remember in that quiz, which is just basically an abstraction of past year questions. If you remember from that quiz, there were bending stresses question, there was a bending deflection question, and I forget there was one more topic. Okay, I don't know if she's trying to drop any hint or something out of the type of topics that are going to be coming out. Start with those. Okay, and then what you can do is from that point work backwards and have a look at the different exam questions from the past papers. Yeah, start off with the ones that have solutions, and then the ones that don't have solutions, you know, compare it with your friends and check. Apart from that, that's it. Okay. If that's all, thanks everyone for attending the revision workshop.
Round of applause for Crash. Recording now. The